Hey everybody, welcome back to Adam P. E21's Garage. Today we go into part 2 of Project All-Wheel Drive E36 XTI. Last episode we talked a little bit about the Subaru DCCD mechanism on the 2004 STI and what we're doing with the ATC300 transfer case for the E36. We took apart the actuator, and today we're going to go into the circuits and sensors that are a part of this actuator and how we're going to use those in a control scheme for 0 to 100% lockup for the all-wheel drive E36. Come along for the ride. So I did a little bit of thinking and a little bit of drawing on this little diagram here. Found this guy online. And basically what this is it's a wiring diagram for the transfer case actuator. You've got different circuits on here. We'll show a picture of that as we go through each of these things. But basically we're going to work on reverse engineering how this actuator works and all the different sensor signals that come out of it. And what I have here is the connector. This comes from the ECU that controls the transfer case actuator. What's odd about this is all the colors, except for the brown wires, which typically are ground in BMW harnesses, they're all different colors than what I'm able to find online for anything with this actuator. But at least with this one, there's a guy in one of the forums helped me out with this, mentioned that this was off of his E90. And basically you've got the two thick wires here. So these are the high current wires that go to the motor circuit. And then you've got some signal wires that are coming off of here. The thick gauge wires are all in the same spots, which is good. And I'm just going to assume that each of these circuits are mounted up in the right holes over here. And that's what we're going to dig into right now, is we're going to characterize each of these signals coming out of here, and we're also going to do some confirmation on the motor. So let's start off with the left side of the diagram here. On the left side, you've got a 2.5 millimeter wire, which is supposed to be red, but it's orange on our connector here. This connects to the positive side of the motor. Then you've got a brown wire that comes from the ground, which is in the ECU here. So that's that brown wire right there. You have a DIR circuit, which even reading up online, wasn't really able to find out what this does. So we're going to do some probing on that signal to figure out what DIR does. That is pin number 6. So if we look at that's 1, 2, 3, 4, 5, 6. So 6 on here is our basically our pink wire. And then we move over to IMP. IMP is a motor pulse. So I'm assuming that is either a once per rev on the motor where you get a Hall sensor pulse or some amount of pulses per revolution on the motor. So that one there is pin number 5. Which is our blue and white circuit here. So this is pink, and this is blue/white. And then we have VCC here, which is coming out of pin number 3. VCC is typically a voltage that comes out of the controller that's for like clean voltage, not noise induced by the motor, filtered voltage coming out of the ECU for sensors and things like that. So that guy looks like it's white, just white there. And then we have what they're calling a temp line, which I believe is a temperature sensor. That's coming out of pin number 7. So that one would appear to be our black and red. So we've got that and red. And then we have a sensor ground coming out of the ECU here, which is like a clean ground. And that's pin number 2. That's this guy right here. So what we're going to do is go ahead and plug in the actuator to this connector. And we're going to do some power up tests. We're going to do some various things here to characterize these inputs. Then we're going to use those as we design how we're going to do a control circuit with this later. Something else I forgot to mention about this schematic here is you've got another 2-pin connector that goes off the end of the gearbox, which mounts up right over here. That is the classification resistor, and I think what it does is when BMW or whoever this actuator supplier is goes ahead and characterizes the actuator, and actually along with the transfer case performance like the clutch engagement areas and so forth, they end up having a classification resistor, which I think serves to give an initial calibration back to this ECU once it's plugged in. I'm not going to do anything with that on this one. This is external to the whole actuator, and we're going to do our own calibration procedure in the ECU that we build here. All right, first things first, we have got to go get a power supply for our system here. And what we're going to do is basically mock up the battery that I've had in the E36 for a while. Very nicely, made in Germany, of course, there. That's good. It's a BMW. It's got to be made in Germany. And we're going to rig up this 12-volt battery basically to be our power supply for all the different things we're going to go ahead and do with this actuator here. So let me get that hooked up here, and then we'll start digging into the voltage on this guy. I'm going to use some of these terminals. You can buy these over at any auto parts store. We're going to slide one end of the jack into here and just tighten this down enough that we've got the jack held in there. We're going to go ahead and mount her up to the negative side here. And we're not really pulling that much current, at least I hope we aren't. So just finger tighten basically on here to hold the terminal on there. We got our negative terminal hooked up there now. Let's go ahead and get the positive terminal hooked up. So one of the important things about using these kinds of terminals is later on, once we start working with the microprocessor and laying out circuits and so forth, we're really going to need something that interfaces well with our breadboard. Let me show you the breadboard we're going to use here. So this is just a pretty standard electronics breadboard. You can buy them on Amazon pretty cheap. But basically, they already have these Pomona connector terminals on here. So what it does is it really makes it easy for us to interface very nicely with our breadboard here once we start laying out circuits. We're not going to get into the circuit design today, but we are going to be using these wires here to basically interface with our motor. And since we have everything plugged in right now as it is, let's just do a quick little test run on powering this motor with the 12-volt battery. So we said the orange was our positive and the brown is our negative. Let's just go ahead and put 12 volts onto this guy and see what happens with that gear. And there we go. So you can see the gear is spinning there, and basically that's what you'd call a 100% duty cycle, straight up 12 volts DC going to this guy, and just keeps on going. So that's good to know. Now one thing looking at the schematic here is if you look closely over at polarization on this side, sometimes with these motors you'll get basically what they call an H-bridge, where you can switch polarity between the positive and negative side to reverse the motor direction. In this case, if you look up here into the microprocessor itself, or into the ECU coming from the car, this here shows that it's connected to circuit 30, which is basically 12 volt or a switched ignition line in the car, and this is showing switched to circuit 31, which is ground. So this indicates to me that this motor only gets 12 volts on this side and only gets ground on this side, and it only spins in one direction. But in order for that to work, one of the things we got to look at is basically our back drive torque on this actuator, because if this actuator can't return to home on its own just from the mechanical forces pushing back in the transfer case, it's not getting home without being powered. And I can tell you right now, just turning it by hand, I cannot back drive this thing. So there's quite a bit of torque that's got to go into this little sprocket here to get that back home, to open up the transfer case basically back to full rear bias. So we're going to dig into this a little bit. Some of the other things that we're going to look at as we look at the terminals on this: the motor freewheeling amperage, we're going to take a look at what that is there. We're going to look at the motor stall current at 12 volts. We're going to look at the pulse per revolution on the motor coming out of that IMP circuit there. And if we get time, we're going to look at the output gear ratio. We're going to measure that or calculate that. And then the output gear revolutions. Once we're plugged into the transfer case, I want to know sort of what home position is at 0, and then what gets us to full lockup there in the transfer case. Okay, what we're going to do here is we're going to take this motor, plug it in, and we're going to have our ammeter wired in series here to determine what our freewheeling torque is. And go to common there. We're going to put her on the 10 amp side right here. Whoops. Now we want to watch our output there as we plug this guy in. So this is going to be on the low side here. We're going to go ahead and connect up to the brown wire here. And then on the positive side, we are going to connect to the orange wire, and we'll take a look at what that current measurement is. Yes. Okay, I guess we're not going to do that. What do we got going on here? I think we're going to have to try another multimeter. There we go. Okay, so this multimeter is running here, and we're going to let her run for a couple of seconds here. But basically, it looks like we're floating between maybe 1.14 and 1.22, 1.23. So we're just going to call it 1.2 amps, and that'll be close enough for what we're trying to do here. So we've got 1.2 amps on the motor freewheel category here. We're going to go ahead and log that right here for later. And let's go on to the next thing. Let's see what the motor stall current is. Now we're going to have to figure out how to do this gracefully here, because you got a lot of torque coming out of this little guy. I'm thinking what we can attempt to do, and it's not going to be as easy as I thought. That's typically how it goes. But I want to just lock this old gear up on here, and yeah, actually, you know what we're going to do? We're going to pull the motor off of here, and as long as that's all still contained, I'm just going to hold on to the end of the motor shaft in there, and we're going to see what this is, the stall current is here, just by the motor by itself. We got all that mechanical advantage of this gearbox here. I might break a tooth or do something goofy on here if this gets messed up. Before we do that though, let's take a look and see if we can back drive this guy. So when I say back drive, what I'm talking about is whether or not in a powered off state, can you turn that sprocket at all? And I can't do that by hand. I'm weak. I'm not as strong as the average human being, obviously, because I can't back drive this. Let's go get a wrench, put one of those on there, and see what happens when we try to turn this. I'm really hoping this can be back driven, because I don't want to have to add the circuitry for an H-bridge in there. Let's just get her across there. See what we got. See, oh, geez, okay. Well, oh, look at that. All right. So, there really isn't much torque going into this guy. I can just barely move it by hand here. Once she starts moving, she moves, and it'll go both directions. It did go both directions. So, the good news is there is some back drivability there. I guess let's see if we can figure out a way to measure the torque on here, just so we know what we're dealing with as far as trying to get a back drive into this from the mechanical system in the clutch. Let me show you real quick, or what I'm expecting to be back driven on this. So you've got our exploded view here, and then basically, as we talked about before, you've got this little actuator down here. This is what our sprocket from the motor interfaces with. There's gear teeth on the back side of this little whirly gig here, and it's spreading these legs out here as it turns, right? So there's a spring force there based off of the clutch plates pressing together up in here, and I'm expecting that to be enough that it can turn this guy to back drive this entire system back to zero. So let's take a look at what the torque is on this guy. All right, until someone can mass market a sprocket-o jobber sort of attachment here, we're gonna have to improvise. I've got a 30, oh boy, I don't know what this is. It doesn't even say what it is on there. What the hang is this? A 35 millimeter socket here from the impact wrench. I think I actually used this for the rear hub and nuts on the E36 when I pulled the half shafts out the last time. And we're going to just go ahead and set some nails in here and hope that these guys are enough to kind of keep the old bit on there. And does it? Yeah, okay, good. Look at that. So it's on there strong enough, I guess we'll say. But basically what we want to do is we're going to put our little inch-pounds, Newton-meters torque wrench on here, and actually I use this for setting pinion lash on my Sonoma. But basically you can see up in the upper left-hand corner there, that indicator moves on there. It's going to be kind of tough to show that as we're going around. Basically I'm able to turn it, I think. There we go. Okay, so the running torque for the back drive here is right about, I'd say, 1.8 Newton meters. So seems to be just a little less than 2. I'm going to say 1.6 to 1.8. But the unlocking torque is actually kind of interesting. There's a little spike there. So let's see what that unlocking torque is. 7, 8. Oh boy, we're going to max this guy right out. 9. Oh, yeah, well, okay. So luckily, about 9 Newton meters is to get that thing to move initially. Go back the other direction here and see what we got for our running torque in the other direction. Yeah, she's about 1.8 there as well. So we got 9 Newton meters of breakaway, and we got 1.8 Newton meters of running torque on there, which seems very, very small. But when you're talking about these kind of gearboxes and these motors, you're talking about millinewton meters of what these guys can put out. These guys don't put out all that much torque. That's why you got this big old gearbox here to work with. But I think 1.8 Newton meters of back drive to get this guy back home, more than enough for that clutch pack and the spring back there to push it back to an open state. So the good news is we aren't going to plan on doing an H-bridge for this guy. We still will plan on doing a 12-volt circuit going into this to power it forward. But I think we also have to think about the PWM side of it, because if you do 12 volts on this and you run the motor to stall it out where you're fully locked up, basically you're going to have to hold it there in order to keep that 100%. So maybe that's why they've got the temperature sensor inside here too, to make sure once you stall that motor, you don't end up overheating this guy. And if you want anywhere between 0 and 100, you're going to have to moderate the current that's going out of this, and you're going to have to use PWM to do that on a DC motor like this. So we'll still end up building a PWM circuit. We'll dig into how this guy acts once we start PWMing that. But let's go into more of the circuitry here and take a look at the pulses coming out of this motor when you power it and you actually move it. Let's go ahead and get this motor pulled off of this gearbox here, and then we'll be able to work with the motor directly. That way we don't have to work through back driving this. We'll be able to back drive that motor pretty easily by hand, unless I've weakened up significantly since the last time I've turned a motor like this. You know, I'm going to have to start working out again because I'm kind of embarrassed that I couldn't turn something that was 9 Newton meters by hand. But, you know, with how sharp these edges are in here, I'd like to see you try to do that without feeling, going past the threshold of pain with your fingertips. So let's see here. All right, well, wait, you know, figures the one I'm missing is the one that I actually want on here. I'm missing this one here. I just, sometimes when I'm trying to look for things and I get in a rush, I lose tools and it ends up just slowing me down, and I could just put the tools away when I'm done with them, but since I don't, it makes it like a treasure hunt actually, and it's kind of fun. Okay, I think we'll just, we'll use this one here. That ought to be good enough to, these guys ought to not be torqued up too much on here. All right. So it looks like you only really have these 2 bolts that hold it to the gearbox, and these 2 guys just kind of hold the motor together there with the end plate, I'm assuming, where there's a bearing and the worm gear coming off of this thing. Let's take a look here if we can get this guy off of here. It's just going to give me a hard time because it knows I'm in a rush, and when you're in a rush you make mistakes, and we don't want to do that. So there we go. Okay, so I'm going to go ahead and just put this guy back in here. Basically, as you saw before when we had this guy apart initially, there's a little plastic worm gear in there. I mean, you know, these are the things that wear out for people in the vehicle, but I don't know, she looks to be in pretty good shape there still. We don't really have any teeth that are ground down or anything like that. The edges are kind of sharp on there, so I don't know. I think it looks good enough that we're going to put it back in. I think it'll be simple enough to change in the car if we ever have an issue after we assemble this thing to swap this motor out. It hangs off the bottom, so it's pretty easy to get at. But anyways, we got this. You can see really easy to turn that on there. you got a lot of mechanical advantage when you got a worm gear like this, and then you got a gear wheel on the inside there. But basically, it's a direct coupling between the shaft coming out of here and that worm wheel that's in there, or that gear wheel that's up inside there. And when you're trying to back drive, you're actually thrusting against the surface here. So that's why it's more difficult to turn something like this by hand with that gear on the inside there. All right, so we're going to mount this guy up here, and we're going to start to apply some power in different areas on this motor and take a look at what these signals do coming out of here. So what we're going to be working with on our schematic here, we're not going to plug in the power to the motor itself anymore, at least for now. And pretty much anything that comes out of this box down here, the sensor board on this motor, is going to be supplied by this small ground here. So this little brown wire right here, yeah, that little brown wire, and then VCC here, which we said was white, that's this guy. So this is going to be our power and ground for this activity where we go through and take a look at what these circuits do on the output here. I'm assuming these circuits, because they show going up to the 30 labeled line here, this bus, I'm assuming these guys are fed with 12 volts. But to be safe, we're going to put a 5-volt regulator on this first, and we're going to make sure that those aren't a 5-volt circuit on there first. All right, this is where things are going to get pretty crazy, pretty weird. So we've got an L7805 little IC here. It's kind of in a FET package. And basically, what we want to do with this guy here is we want to regulate our 12-volt voltage coming from the battery over there to a 5-volt clean signal coming out. And you need power, ground, and basically just power and ground going to this guy. And the output from this is a 5-volt signal. Pretty simple. So we're going to plug in power and ground. I'm pretty sure it goes power, ground, and then out. But basically, we're going to do these two terminals connected up over to the battery power supply, and then we're going to run this 5-volt signal over to the VCC line. Now, I wasn't expecting to get into the breadboard tonight, but since it'll be easier to hang on to this 5-volt regulator, we're going to go ahead and wire up this guy to the power rail here right now, and touch this guy here just to make sure we're not burning anything up. And nope, she's hopefully regulating just fine. And let me find, I guess I've got these broken connectors here that I can use. We'll switch this guy over to 20 volts there. And let's take a look at what we've got coming out here. Let's confirm we got 12 volts in there first. Yep, we got 12, oh boy, 13 volts. Look at that, that's a strong battery. And what do we have here? Look at that, oh, 4.6. Well, it's not the 5 I was looking for. But, you know, I guess, I was hoping that would be, oh, interesting. When I touched it, maybe I need to ground that guy out on the tab here. We're at 4.6 volts, 4.5. I think that'll still be good enough for what we want to do with the actuator over here. So we're going to use this 5-volt, 4.5 volt circuit here right now and see what these sensor outputs start giving us. Anyways, we're going to take the brown wire here and run that into our 5-volt output. Oh, no. I don't want to do that. Gee, I'm in a rush, and see, that's what happens. You make mistakes when you get in a rush. And when you don't have time, you rush a lot more. And it just, yeah, it's not going to do what I want it to do down here. I've got, you know, I didn't even think about this. This is the simplest way to do it, and I'm going to do it this way because, you know, we're going to watch that voltage on there, make sure she doesn't do something screwy when I go ahead and hook up our ground here. It's probably going to be a little crazy here at first, but let's just get this guy put in here. Okay, and then we're going to go ahead and put our white wire on the 5-volt side. And hopefully we don't see anything smoke or blow up or, you know, anything like that, because if it did that, then I'd probably be pretty unhappy, because that means I would have burnt up a circuit in here. This is good. So I think what happens is, if you don't have a load on this 5-volt regulator here, now we've got a load on there, it'll just want to sit there and kind of float. Now that we have a load, she's sitting there right nice at 5 volts. All right, so I guess the first circuit we're going to look at, and I'm going to use my other voltmeter here, provided it can actually measure voltage instead of the amperage the last time, which wasn't working for us. But we're going to keep an eye on this 5-volt circuit here just to make sure she doesn't dip. If it does, we know that we've got a short somewhere, and that's not a good thing. And what we're going to look at now is the outputs from our circuits here. Now, one thing that we're going to have to be careful of is these may need something like a pull-up resistor in the ECU side in order to keep it from basically floating when it, you know, it'll draw it to ground as a low side drive type sensor, but then it'll also, you know, need something to pull it back up to 5 volts, or it actually, based off of the schematic, and this is convincing me more and more that this has got to be 12 volts going into VCC instead of 5. But basically, all the pull-ups on here are going back to 12 volts. And effectively what happens here is when, let's say on the impulse side here, when the sensor triggers to say that it's hit the sensor for the revolutions, it's actually going to pull the signal to ground, and then it takes this line that goes back to the ECU, the one with the arrow on it, and basically pulls that to ground. When it's open, what happens is it gets pulled up to power. So think of it this way: when it pulls it to ground, it's basically going through a resistor here. It pulls this guy right down to ground. When this guy's open, going through that resistor, you shouldn't have any current, and basically it takes it right up to that 12 volts. All right, let's take a look at the impulse one here first. I've got a 10K resistor here. I'm not going to go into detail as to how to read the codes out on these because they're color coded there. Go get an electronics degree if you want to know what the code is on here. But the 10K resistor ought to be big enough that we're not going to overcurrent the little sensor inside this guy, and it should be small enough that we pull enough current in order to basically trigger the signal here as it's being actuated. So like I said, we're going to go ahead and connect this guy up to the 12 volts on the upper rail here. So we got that resistor going up to 12 volts. Right now, basically, this guy, if it's an open circuit, should be reading 12 volts. If it's a closed circuit, it'll be reading ground. But let's go ahead and put this on there. We got 8 volts. That's odd. Oh, but look at that. So you can see it's basically toggling between, let's say, 8.5 volts and 0.8. So it makes me wonder if it doesn't have to be 5 volts going into VCC there. I bet you that's got to be 12 volts going into VCC, and we're probably not getting the full power that we want out of this guy here. So we're going to go ahead and connect what we had for our 5 volts here up to 12 volts, and then we're going to do the same thing we just did. And I'm going to disconnect this 5 volt circuit here because I don't want to mess something up if I end up going into, well, you know what, I'm going to leave the 5 volts on there. But it means that we got to get that guy out of there. Yeah. Okay. All right. So we got 12 volts going into VCC now. Still 8.5. That's interesting. But it's going between basically 0.8 and 8.5. So that tells me that as you index this motor shaft, you're going between 0.8, 8.5. So we need to count how many revs we get out of the motor for every pulse that comes back on this guy. But at least for now, we're going to go ahead and document the fact that we've got an impulse, we've got, it's going 0.8 to 8.5 volts. We still didn't answer the question whether or not we've got a 5 volt or an 8 volt, a 12 volt going into that, but it's doing the same thing whether we have 12 or 5 plugged in there. I think in order to make sure that we don't end up drawing too much current through this guy or getting a 5 to 12 volt short somewhere, we're just going to leave that put right at 12 volts there for now. So now what we want to do is we want to define where our starting point is on the motor shaft here. Probably going to have to score a little line or something on there just so we know where it is. And then we're going to count how many times that guy pulses down to 0.8 in one revolution of the motor. Okay, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we've got 10 pulses basically on this half here. We're just going to assume that there's 20 pulses around this entire rotation of the motor, and that'll be important when we come up with the control scheme later on, because we're going to want to know how many times this motor is rotating so we can know exactly how much this guy on the outside here rotated as well. You look at this worm gear, one of the next things we want to do is understand what our gear ratio is coming off of the motor here. How you do that with a worm gear like this, you got to look at the end of this guy here, and as you can see, there is 1, 2, 3 starts on there. So you got 3 starts on this worm gear here, and if we're lucky, yikes, it's going to be fun to figure out how many teeth are on this guy here without taking this guy apart. Actually, not going to be too bad. So we're going to go ahead and pull this apart here. We've got 3 starts on this guy, and we're going to count the teeth on that worm wheel inside there. And of course, I don't have the right size for this one. This is going to have to do here, I guess. Oh my goodness gracious. Well, I was wrong. There's actually a little planetary gear set inside this thing, which further reduces our gear ratio even more. So we've got quite a bit of math we got to do here. Awesome! Anyways, let's start with this guy then. And let's count how many teeth we've got around our main wheel gear here. And we're going to start right where that little grease blob is right there. We got 1, including the grease blob, 2, 32, 33, 34. We got 34 on this guy. And actually, what's interesting is this is metal. I always thought these things were plastic in here, but that guy is definitely metal. And that worm gear on the end of our motor shaft is also metal. So I don't know if this actuator was replaced once before or not, but I had heard that there were issues with these guys stripping out, but we got metal on metal, and I'm happy to see that. So we said 34 right there, and we have 3 starts on the worm gear. So let's write that down before we forget it. And then in our planetary gear set, let's take a look at this, 11. And inside here, we've got 1, 13, 14, 15. So we've got 11 and 15 in our planetary gear set. All right, let's get this guy put back together so we don't get muck and stuff inside of here. And we'll go ahead and calculate out those ratios on the side. Oh, this is going to be a lot of fun. This is going to be a lot of fun getting it back together. This, I wasn't expecting to have this much fun. Yeah. This is so much fun that, you know, it's just not going to go back together as easily as it came apart, which indicates to me that we're going to have a lot of fun putting this guy back together. This is fantastic. Yeah. Ah, yes, look at that. Okay, perfect. But what? There we go. Okay. let's get this guy put back together. I don't ever want to have to look inside this thing ever again. I just, you know, there's nothing appealing to me about what I saw inside of there, except that we figured out that we have a planetary gear set, a planetary gear set inside this thing, which just further complicates our calculations. But, you know, we're doing the right thing here by going this in depth, because if I'm going to take this thing out on the trails, I want to make this as complicated as possible, so if something breaks, it's really hard to fix it underneath the car, laying in mud or ice or sand or on the lunar surface, anything like that. And we want to make this as complicated as possible. That's the only way to make this work right, is to just complicate things as much as possible. It will just, you know, okay. So let me just restate here why it's important to look at these ratios, why we're looking at the pulses per rev on this motor output. When you create a control system for something like this, the only way you know where this guy ends up, there's no potentiometers in here like you have with a throttle position circuit, nothing like that. You've got to count the pulses on here, that motor shaft output, and do some math with those ratios to figure out exactly how far this guy has moved. And then we're going to have to calculate out of that exactly how far this little guy moves on here to index the clutch mechanism in there. And why that's important is I'm going to establish limits in the controller. So if I count too many pulses or too little pulses, I know there's something mechanically going on in here, there's something going wrong with the system, and we're going to fault out the system and make sure it goes back to a home position. But the other thing that we have to do is we're going to have to measure current, we're going to have to measure the pulse outputs on this and everything while this thing is working in the vehicle, so we know exactly where the 0 position is and where the 100% lockup position is. And effectively we have to calibrate our controller and the PIC controller and the software to know where 0 and 100 is, so we can go anywhere in between that based off of counting how many pulses come out of this guy, and by monitoring the current on there as well. So we're going to get way into detail on that stuff when we go ahead to implement this. But laying the groundwork here, let's see what DIR does, which is, that is our pink wire. I got so excited when we were doing this before, I lost my pull-uppers. There we go, okay. So on our pink wire here, we're going to couple that to this guy here again. I'm sure the grease on these, on my fingers, is really making for a nice clean connection when we do this. But you know what? That if you're going to do this in your garage, you can't expect to have pristine, clean hands that are just going to, I don't even know how to explain it. I'm just so terribly excited that we're going to come up with a solution on this. Well, you know, I think we're only getting 1 pulse per rev on that guy. But when I spin it the opposite direction, she stays at 8.5. If I spin it this way, okay, now we're starting to, things are starting to add up here a little bit. So I think DIR, while not something that would be German, I think that tells us what direction the motor is moving. If I go this way, if I go counterclockwise on the motor shaft, it stays at 0.82. If I go clockwise on the motor shaft, it stays at the higher voltage there. So, except for that part right there. No, I just went back, that's why. So yeah, I guess this is a directional signal. If I keep it going fast enough, it stays up there. If I go the other direction, it goes low. So we've got, looking into the motor shaft here, if I go counterclockwise, it goes to 0 or to 0.8. If I go clockwise, it goes to 8. So that will be helpful to know which way the motor is spinning, because when this guy gets back driven, then what's going to happen is I'm going to watch the pulses and see that this voltage goes low and know that it's being back driven back to a home position. So DIR is 0.8 8 in counterclockwise and 8.5 in clockwise. So when you've got the proper polarity on there, she's going clockwise. If we were to reverse that, she's going counterclockwise. So when this guy is going clockwise, that's when we've got the positive signal. Again, to double check what we figured out here, if she's going clockwise, that's high. Counterclockwise, it's low. Dang it, I did it again. Let's look at what this little temperature circuit is telling us over here. So that was our black and red wire coming out of there. And again, we're probably going to have to put a pull-up on this guy. But that temperature circuit isn't telling us anything right now. And do our little 10K pull-up here to this temp line. What do we got? Nothing. Why? Because this guy fell out. There we go, look at that. 2 volts right now, and nothing is changing there. So I'm assuming there's maybe like a little thermistor or something inside there. Let's see if the voltage goes up or down on this as this guy heats up. All right, let's see here. Well, we don't have much heat coming out of this thing. Good for nothing. Okay, so she's heating up there. Number continues to get higher as that hair dryer is heating it up. Started out at about 1.95 or so, and as this guy warms up and as we're running it, she's going up in temp. That's good to know. Probably about 45 degrees Fahrenheit in the barn right now. Okay, that is enough of that. I think we figured out that the temperature will go up. There's a voltage output. We'll be able to monitor that with the ECU, and we'll just have to figure out what that temperature range is. That'll be something I'll have to do offline, where I'm going to have to heat this up in an oven, try to figure out what the specs are for this motor before it overheats. But we'll take a look at that in another episode. So while we got this guy mounted up here, we're going to go ahead and do a stall current check on the motor. She's nice and warm. I would just say, yeah, that's probably about 90 degrees Fahrenheit. I don't even know if it's worth writing that down. But we'll just say after the hair dryer it was 2.41 volts. And I'll remember what that felt like. So let's go ahead and hook up our ammeter again. We're going to just disconnect this guy right now. And actually we're going to go ahead and disconnect our VCC as well. We've looked at all the circuits, and the last thing we're going to do here is now characterize what is going on with the stall current. And I think we're going to call it a night on that. Get her, whoa boy. Let's go ahead and load her up. Yeah, I'm not going to be able to do that by hand. I think what we're going to do, we're going to do something really dumb here and basically put the end of the motor shaft into here and just kind of do that. And I'm going to hang on to this, and I'm going to try to keep this guy from jumping all over on us. Oh yeah. Oh boy. So she's got more than 10 amps coming through there when it stalls. I'm not going to be able to measure it with this ammeter. So basically I think what we're going to have to do to really figure out what kind of current we got going through there. Oh boy. maybe we could just stall this guy at 9 volts, or whatever voltage I got in this little battery, wherever that went. We got her running at 9 volts. And let's stall her. There we go. At 9 volts, she's about 2 amps, and it goes down because it's warming up. So at 9 volts, actually whatever voltage this guy's at, which we should double check what this voltage is. We had 2 amps when we stalled that thing out. I'm killing this battery, by the way. Okay, 4.5 volts is what's coming out of there right now. I'm going to stall this motor, and the battery's basically dead. 2 amps at 4.5 volts. Let's just take the, yeah, that math isn't going to work out. I got to figure out a different way to measure current on this so we know what the stall current of this beast is. I think what we're going to do is we're going to end up buying some current measuring chips, probably a 20 amp or a 30 amp current measuring chip. We're going to figure out what the voltage is on that, and we're going to build up a circuit on the breadboard here in a future episode and figure out what that stall current is. All we know right now is that this maximum stall torque is greater than 10 amps at the 12 volts that we had there. All right, guys, so I think we've pretty well characterized what we wanted to do tonight with this motor. Okay, so that's going to be a wrap for this video. We've made a sufficient mess down here on the bench, and we've got the good groundwork laid here for a lot of the electrical parameters that we're going to be dealing with. So I think we're going to go ahead and call it a night with this one. We're going to be thinking about how to do the control system as we're wrenching underneath the car. Eventually we'll get into pulling the subframes off of the E36. We'll get a new diff put in the rear end. We've got a Z3M diff lined up with that, with the Quaife differential in it. And then we're going to take the M42 engine out, drop the front subframe, drop the rear subframe, get it all cleaned up underneath there. And then we're going to figure out how to get that E46 drivetrain and front subframe and suspension mounted up. Thanks for watching, everybody. Don't forget to like and subscribe. Really appreciate you guys watching. I'm looking forward to this year. It's going to be exciting. We're in it for the long haul with this car, but it's going to be great when it's finished. Thanks again.